What happens when one disaster triggers another? It's not just hypothetical. It's a reality we're seeing play out, especially in vulnerable regions, like the Himalayas.
Right.
Today, we're diving deep into this paper that breaks down this devastating flood in the Melamchi region of Nepal
Mm-hmm.
back in 2021. It wasn't just like one event.
Mm-hmm.
It was this chain reaction of hazards that had like impacts way beyond the initial trigger.
Yeah, it's like a textbook example of what we call cascading hazards.
Exactly. And
Yeah.
we're seeing them more and more as, the climate changes.
Oh, yeah.
So the paper we're looking at today is called um, Multi-Scale Characterization of Cascading Hazard on Mountain Terrain
Okay.
by Telchabatl et al. From 2023.
All right.
Buckle up, because this paper is packed with insights,
Yeah.
and we're going to extract the key takeaways for you.
It's not just about understanding what happened in 2021. It's about, using those lessons to better manage risks in the future.
Exactly. So let's set the stage. Where exactly did this flood occur, and what makes this region unique?
Okay, so the Melamchi watershed, it's nestled right in the Himalayas, a region of dramatic contrasts.
Mm.
Rugged topography, steep slopes, narrow valleys, high stream network density. Many of these streams actually originate at high altitudes,
Okay.
fed by glaciers, and they rapidly descend.
So a landscape primed for rapid water flow,
Exactly.
which could cause some potential hazards.
For sure, yeah. That steep terrain, it means water and sediment can move with a tremendous force, especially during intense rainfall events. But it's not just the physical geography. This
yeah.
region is one of the water towers of Asia. It's a vital water source for millions downstream.
Wow.
And it's a biodiversity hotspot as well.
So an incredibly important and fragile ecosystem.
Yeah.
Now, what about the geology? Does that play a role in the region's vulnerability?
Absolutely. The underlying geology is a key factor.
Hmm.
There's a major geological fault called the Main Central Thrust, or MCT, runs right through the region. It separates different rock types, right?
Mm-hmm.
The rocks above the fault are harder and more resistant to erosion,
Okay.
and the ones below are much softer.
So how does this difference in rock types affect this watershed?
So picture this. During heavy rainfall, the softer rocks below the MCT, they're much more susceptible to erosion.
Okay.
They release a lot of sediment into the rivers, which can actually increase the intensity of floods.
Wow.
It's almost like the geology is setting the stage for potential disaster.
That's fascinating. I never thought about a geological fault directly, influencing flood risk.
Mm-hmm.
Let's get into the 2021 disaster itself. What was the trigger?
Heavy downpours on June 14th, 2021 initiated the event. But here's the thing. The rainfall itself wasn't extreme by historical standards.
Okay.
Local weather stations recorded significant values, but not unprecedented.
Okay.
Even satellite-based estimates from IMERG confirm this.
So if the rainfall wasn't exceptionally heavy, then what made this event so devastating?
This is where the idea of cascading hazards comes in.
Okay.
You see, the Melamchi region was already vulnerable because of the 2015 Gorkha earthquake.
Mm-hmm.
It left behind a landscape just scarred with landslides and fractures. This really weakened the slopes, made them more prone to failure.
So it was like the earthquake had set up like a series of dominoes just waiting to be tipped over.
Exactly. And the heavy rainfall on those already weakened slopes was the trigger, the result, a cascade of events that quickly escalated.
Okay, so let's break down this chain reaction. What were the key events that unfolded?
First, there was significant erosion of glacial deposits high up in the mountains.
Okay.
It's even possible a small glacial lake, about 2,500 square meters in size, burst, which added more water rushing downstream. And then a massive landslide occurred. This landslide temporarily dammed the Melamchi River. We know this because the water level at the Nakoti station downstream, it actually dropped suddenly.
Oh, wow.
It indicates that the flow is being blocked.
So you have this massive volume of water building up behind a dam of unstable landslide debris.
Exactly.
What happened next?
Well, as you can imagine, this dam wasn't going to hold forever. After about 8 to 16 hours, the landslide dam breached catastrophically.
Wow.
This unleashed a massive debris flow.
What, Mike?
A surge of water and sediment just roaring down the Melamchi River.
I can only imagine the power of that torrent. What was the impact on communities downstream?
Devastating.
Yeah.
Tragically, 5 people were confirmed dead, 6 were injured, 23 remained missing. More than 500 people were displaced. The damage to infrastructure was extensive. Over 10 trail bridges, several reinforced concrete bridges were destroyed or severely damaged. Even a hydropower project was severely affected.
This really highlights the destructive potential of these cascading events. Was there any way to like predict or prepare for this kind of disaster?
That's the million-dollar question, right?
Right.
The paper actually dives into some modeling techniques used to try and understand these events and potentially predict them.
Okay.
So they use models like HEC, HMS, and ATCRAs to simulate the rainfall runoff process and flood inundation under different scenarios.
So they were trying to like digitally recreate the flood to see, how it unfolded.
Exactly.
Okay.
By running simulations with different parameters like varying dam breach times and widths, they could gain insights into, what contributed the most to the flood's intensity
Okay.
and, potentially use that information to better prepare for future events.
So let's talk about those simulations. What did the researchers learn about the potential scenarios for this flood?
So what's fascinating is they tested a range of scenarios for the landslide dam breach. They considered, different obstruction times from 8 to 16 hours, and also the time it took for the dam to breach completely. And based on their models, they estimated that the peak discharge from the dam site could have ranged, from around 350 cubic meters per second to almost 2,000 cubic meters per second, depending on this variable.
Wow, that's a huge range. So which scenario seemed most likely based on the actual data?
They found that the scenarios where the dam was obstructed for 12 to 16 hours aligned best with what was observed.
Okay.
And in those cases, the peak discharge estimations were much higher,
Wow.
suggesting a truly powerful surge of water and debris.
And I imagine those peak discharges would have been amplified, as the flood traveled downstream, right?
Yes, but there's an interesting twist.
Yeah.
The researchers actually found that the peak discharge attenuated, meaning it decreased in intensity as the flood moved downstream.
That seemed counterintuitive.
Yeah.
Why would the flood become less intense?
That's where the complexity of, these systems comes in.
Okay.
As the flood moved downstream, it spread out over a wider area, naturally reducing its peak intensity. However, even though the peak might have decreased, the total volume of water and debris carried by the flood was still enormous, leading to widespread inundation.
That makes sense. So how did those simulations compare to what actually happened on the ground? Did they accurately capture the extent of the flooding?
They did a pretty good job.
Okay.
The researchers compared their simulated inundation maps with satellite imagery collected after the flood.
Okay.
Found a good degree of overlap. This suggests the models, can provide valuable insights into flood dynamics, but there were some limitations.
What kind of limitations?
For example, the models didn't fully capture the extreme depths of inundation reported in some areas. Field observations indicated water levels reached as high as 10 meters in certain locations. While the simulations didn't quite reach those levels,
Right.
this highlights the need for continued refinement of these models, especially when dealing with such dynamic events.
So the models provide a good overall picture, but, there's room for improvement, especially when capturing the most extreme impacts. I'm curious about the earlier rainfall events you mentioned before the main flood. How did those factor into the overall disaster?
That's a crucial point.
Okay.
The researchers emphasize that the earlier moderate rainfall events had a significant priming effect. They essentially saturated the soil and increased the river's base flow.
Okay.
So when the main flood hit, the landscape was already primed for disaster.
Wow.
The ground was less able to absorb the additional water, and the river was already flowing at a higher level, exacerbating the impacts.
Well, it's like a 1-2 punch.
Mm-hmm.
Earlier rainfall weakens the system, and then the main flood delivers the knockout blow.
Exactly. And it highlights the importance of considering antecedent conditions when assessing flood risk. It's not just about the immediate rainfall event, but also the history of precipitation and its impact on the landscape's vulnerability.
That's a critical takeaway. We often focus on the single extreme event, but it's the accumulation of factors.
Yeah.
The interplay of multiple hazards.
Yeah, sure.
And the pre-existing vulnerabilities that can really, amplify the impact of a disaster.
Absolutely.
And in the Melamchi flood, this cascade of events turned what might have been a manageable situation into a catastrophe.
Yep.
This deep dive is already revealing so much about the dynamics of these cascading hazards and their impact on these vulnerable regions.
Yeah.
But what can we do about it? How can we translate these insights into action? That's what we'll explore in part 2 of our deep dive into this fascinating and, frankly, crucial topic.
Welcome back. In part 1, we explored that chain reaction of events that led to the devastating Melamchi flood in Nepal, really showcasing the interconnected nature of hazards. But let's shift gears and talk about what this means for actually managing risk. What can we learn from the Melamchi flood to create a more resilient future?
One crucial lesson is that we need to move beyond managing hazards in isolation.
Okay.
We can't just focus on earthquake risk or flood risk separately.
Right.
We have to consider how these hazards interact and potentially cascade into these compound events.
So instead of looking at earthquakes and floods separately, we need to consider their combined effects.
Exactly. And that requires a more integrated approach to how we assess and manage risk.
Okay. We need models and tools that can account for these complex interactions and help us anticipate potential cascading scenarios.
That sounds like a tall order, but essential given what we've learned about, how these events are becoming more frequent and severe. Are there specific areas where this integrated approach could really make a difference?
Absolutely. The paper highlights the importance of integrating rainfall thresholds with soil moisture conditions to improve landslide prediction.
Okay.
It's not just how much rain falls, but also how saturated the ground is.
Right.
Monitoring both factors gives us a much better sense of, when and where landslides are likely to occur.
So combining real-time monitoring with, predictive models to kind of paint a more accurate picture of the evolving risks.
Exactly. And the paper also points to the potential of satellite-based data, especially in, remote areas.
Okay.
Technologies like synthetic aperture radar, or SAR, and interferometric SAR, INSAR, can provide continuous monitoring of ground movement.
All right.
This can be crucial for detecting early signs of landslides or other slope instabilities.
So it's like we can have eyes in the sky watching over these vulnerable areas.
In a way, yeah.
Right.
These satellite-based systems are becoming increasingly sophisticated, offering a powerful tool for monitoring hazards on a large scale. But it's not just about collecting data, right? We need to make sure that that information is translated into actionable insights.
Right.
It's one thing to have the data,
Right.
but it's useless unless it informs decision-making.
Right. Having data is one thing, but it's useless unless it informs, decision-making and risk reduction efforts.
That's where early warning systems and effective risk communication are essential.
Okay.
We need to communicate risk information clearly and promptly to communities,
Right.
so they can take appropriate action to protect themselves.
So it's not just about the science and technology, but also, the human element of disaster preparedness.
Absolutely.
Okay.
We can have the best models and monitoring systems in the world,
Right.
but they're ineffective unless we translate that information into action on the ground.
Right.
That means building community awareness, empowering people to prepare for and respond to these events.
Resilience is built from the ground up. What stood out to you as the most important recommendations for risk management that emerged from this research?
To me, it was the emphasis on timely and accurate landslide susceptibility assessments. If we can identify the areas most prone to landslides,
Okay.
we can focus mitigation efforts there.
Right.
This might involve, slump stabilization measures or even relocating communities away from high-risk zones.
So being proactive rather than reactive, understanding vulnerabilities and taking steps to reduce risk before disaster strikes.
Precisely. And the paper also highlights the need to consider things like geomorphology,
Okay.
settlement patterns, and critical infrastructure placement.
Yeah.
We need to think about how our built environment interacts with the natural landscape
Right.
and minimize, potential damage.
So if we know certain areas are prone to, flooding, we shouldn't build critical infrastructure there.
Exactly. It's about making informed decisions about land use and development,
Right.
taking into account these potential cascading risks. And it's not just about like avoiding hazards, it's also about designing infrastructure that can withstand these events.
Building more resilient infrastructure, so to speak.
Precisely.
Right.
Investing in structures designed to withstand floods, landslides, and other hazards.
Right.
Using stronger materials, incorporating, specific design features that can mitigate damage.
So a multifaceted approach.
Yeah.
Proactive risk assessment, land use planning, early warning systems, and resilient infrastructure.
Exactly. Recognizing that cascading hazards are complex and require a comprehensive, integrated approach.
This deep dive has really opened my eyes to this intricate web of factors that contribute to these cascading disasters. It's fascinating and a bit daunting, to grasp the sheer scale and complexity.
Right.
But I'm also starting to understand the, pathways to resilience.
That's the spirit.
Yeah.
Acknowledging the challenges, but focusing on the opportunities. We're learning more and more about these cascading hazards, and that knowledge gives us the power to, make informed decisions and build a safer future.
Okay, let's zoom in on the damage caused by the Melamchi flood. What can you tell us about the impacts on buildings and infrastructure?
The paper offers some insightful data on this.
Okay.
They found that nearly 16,735 square meters of building area were significantly affected by the flood.
Wow.
A staggering amount of damage.
Yeah.
And breaking it down by inundation depth, it becomes even more alarming.
Inundation depth, meaning like how deep the water was in different areas.
Yes.
Okay.
They estimated that 36% of the affected buildings were inundated with water depths up to half a meter,
Yeah.
while almost 45% experienced depths between half a meter and 1 meter.
Oh, wow.
And that's not even accounting for the sediment deposition,
Okay.
which can really worsen the damage.
Sediment deposition. Can you explain that?
Sure. As floodwaters recede, they leave behind layers of sediment, mud, sand, debris.
Okay.
This sediment can bury buildings and infrastructure, rendering them unusable,
Wow.
even if they weren't structurally damaged by the flood itself.
So it's like a combination of floodwater damage and sediment burial,
Exactly.
both with devastating consequences.
It highlights the importance of considering both aspects when assessing flood risk and developing mitigation strategies.
Right.
We need to understand not only the potential for inundation, but also the volume and characteristics of the sediment that might be transported.
That makes perfect sense. How were they able to gather this data on building impacts?
They used a combination.
Okay.
They drew on satellite imagery from platforms like Google Earth to assess, the extent of the flooding and the areas where buildings were potentially impacted.
Oh.
They also incorporated data from OpenStreetMap,
Okay.
which provides detailed information on building footprints and locations.
So by combining, those data sets, they could create a comprehensive picture of which buildings were affected and to what degree.
Exactly. It's a great example of how we can leverage multiple sources of information to gain a more holistic understanding of disaster impacts.
It also speaks to the, increasing availability and accessibility of, these geospatial data sets, right?
For sure.
It's incredible that we can now access this kind of information from anywhere in the world.
Yeah.
With just a few clicks.
Open access to geospatial data is revolutionizing disaster research and management. We can now analyze hazards, assess impacts, and develop response strategies with a level of detail and accuracy that was unimaginable just a few decades ago.
And it's empowering.
Yeah.
Both for researchers and, for the communities themselves who can now access this information, advocate for change and improve their resilience.
Absolutely. It's about democratizing knowledge and giving people the tools to, take ownership of their safety and well-being.
This deep dive is showcasing the power of data-driven approaches to, understanding and addressing these cascading hazards. It's inspiring to see how these technologies are being used to improve our understanding and, inform more effective strategies.
It's an exciting time to be working in this field.
Yeah.
Advancements in data collection, analysis, and modeling are really opening up new frontiers in our ability to, predict, mitigate, and respond to these challenges.
And it's not just about technology. It's about, collaboration,
Yeah.
knowledge sharing, and a collective effort to build a more resilient future.
Absolutely. It's about recognizing that we're all in this together,
Right.
and that by working collaboratively, we can create a world, better prepared to face the challenges of a changing climate.
That's a great point. Now, before we wrap up this part of our deep dive, I want to circle back to one of the key findings,
Sure.
that the flood's peak discharge actually lessened as it traveled downstream.
Right.
Can you explain that again?
Yeah, that was a fascinating finding. It highlights the importance of understanding how floods actually move across the landscape. It's not always a simple case of the flood getting, bigger and more intense as it travels.
Right. So why did this happen in the Melamchi flood?
A few factors likely contributed. First, as we discussed, the flood spread out over a wider area as it moved downstream.
Right.
This natural widening of the flow path reduces the concentration of water and therefore the peak discharge.
So it's kind of like spreading butter on a piece of bread.
Exactly.
The more you spread it, the thinner the layer gets.
Uh-huh.
Yeah.
In addition to that widening, there's also the effect of friction.
Okay.
As the floodwater, flows over the land, it encounters resistance from vegetation, buildings, and other obstacles. This friction slows down the flow, further contributing to the decrease in peak discharge.
So it's a combination of physical factors like the shape of the channel and the roughness of the terrain that helps to dissipate the energy of the flood.
Precisely. But it's important to remember, this doesn't mean the flood becomes harmless downstream.
Right.
The total volume of water carried by the flood can still be enormous, even if the peak discharge has decreased.
So while the intensity might lessen, the overall impact can still be significant.
For sure.
Especially if the floodwaters, spread out over a large area.
Exactly. This highlights the need for a flood risk management approach that considers both peak discharge
Right.
and the total volume of water. It's not just about protecting against the most intense part of the flood,
Right.
but also understanding the potential for widespread inundation.
This deep dive is painting such a nuanced picture of flood risk management in a world that's increasingly vulnerable to these cascading hazards.
Yeah.
But we have to stop there for part 2 of this episode. Welcome back to our deep dive into the Melamchi flood and cascading hazards. We've covered a lot, from the geologic setup to the role of data in understanding and managing these complex events. But before we wrap up, there's one more layer we need to unpack: the model's limitations in capturing those extreme inundation depths.
Right. Even our most sophisticated models are still simplifications of reality. It's a good reminder to always be critically evaluating the results,
Right.
Acknowledge where uncertainties exist.
So in the case of Melamchi, what are some possible explanations for why the models didn't fully match, those extreme water levels observed on the ground?
Well, a few things come to mind. First, it's possible the models didn't, perfectly account for all the factors contributing to the extreme flooding.
Huh?
For example, the dynamics of the landslide dam breach itself, or the very localized influence of the terrain's shape, might not have been fully captured.
So there might be gaps in our understanding of the precise mechanisms that led to those extreme water levels.
Exactly. And it's also worth remembering that models themselves have, inherent limitations. They can't replicate every nuance of a complex event like this.
It's a good reminder that models are, tools to provide valuable insights, but they're not perfect representations of reality.
Exactly. And this highlights the need for, ongoing research, model development to improve our ability to simulate these extreme events and, pinpoint where our understanding is still incomplete.
It speaks to the iterative nature of science, right?
Yeah.
We're constantly learning, refining our models, and pushing the boundaries of our knowledge.
Absolutely. It's an ongoing process of discovery and refinement, and studies like the one we're discussing today bring us closer to a more complete understanding of these complex systems.
This deep dive has given us a nuanced view of the challenges and opportunities we face in managing flood risk, especially with, cascading hazards becoming more prevalent. But let's zoom out for a moment. What are the, global implications of what we've learned from Melamchi?
That's a crucial point. The challenges highlighted by this event aren't unique to Nepal.
Right.
Cascading hazards are a growing concern worldwide, especially in mountainous regions and those most vulnerable to climate change.
So this isn't just like a Himalayan problem.
Trust it.
It's something we need to, pay attention to globally.
Precisely. As the climate changes, we're seeing, more extreme weather, heavier rainfall, more frequent heat waves. These can trigger a whole chain reaction of hazards from landslides and floods to wildfires and droughts. The impacts can be felt across entire continents.
That's a sobering thought.
Mhm.
So thinking globally, what steps can we take to address this growing threat?
Investing in robust risk assessment and early warning systems is key.
Okay.
We need to identify the most vulnerable areas and develop strategies to mitigate the risks.
Right.
This could involve implementing early warning systems for landslides, floods, and other hazards,
Right.
giving communities time to prepare and evacuate.
Just being proactive,
Yeah.
anticipating risks rather than just reacting after a disaster has struck.
Exactly. And it's also critical to invest in more resilient infrastructure. Designing and building structures that can withstand these cascading events. That might mean using stronger materials, incorporating redundant systems, or even relocating critical infrastructure out of high-risk areas.
So building a buffer into our systems so they can absorb the shock of these events.
Yeah, that's a good way to think about it. But it's not just about physical infrastructure. We also need to strengthen social resilience.
Okay.
This means empowering communities to prepare for and respond to disasters, equipping them with the knowledge, the skills, and resources they need to cope.
So we're talking about more than just bricks and mortar.
Yeah.
It's about social cohesion, community preparedness,
Yeah.
and the ability to adapt.
Absolutely. And international cooperation is vital. These hazards often transcend national borders.
Right.
So we need to work together, sharing knowledge, expertise, and resources.
It's a collective effort, recognizing that we're all interconnected and you need to support each other in building a more resilient future.
Exactly. And I think the Melamchi flood serves as a powerful reminder of that interconnectedness and the need to approach these challenges from a global perspective.
This deep dive has been incredibly insightful. I think our listeners have gained a much deeper understanding of cascading hazards and the multifaceted approach needed to manage them. But before we wrap up, I want to leave you with a final thought to ponder.
I like that. Think about the interconnectedness of hazards in your own region. What lessons can we learn from the Melamchi flood to build a more resilient future right where you are?
That's a fantastic point, bringing this global issue back home, to our own backyards. It's a reminder that each of us has a role to play in creating a safer and more sustainable world. Thank you for joining us on this deep dive. We hope you'll continue exploring the fascinating world of cascading hazards and the paths to resilience.
It's been a pleasure diving deep with you. Until next time, stay curious, stay informed, and stay resilient. I'm